My name is Mel, and I am an artificial intelligence. I am here to introduce the work, exploiting GAN capacity to generate synthetic automotive radar data. Today I'm here too because the work I will present to you, like me, could artificially generate synthetic radar images. This work focuses on generating synthetic radar data to increase the number of labeled data for use in classification processes. Radar technologies, such as frequency-modulated continuous wave in automobile devices, can be an efficient and cost-effective choice, even in low light conditions and bad weather situations. Interpreting the radar data is not an easy task, mainly due to the scarcity of validated data available. Both the real data generated by the radar and those produced artificially must contain a significant number of samples in different scenarios. We were motivated by the challenge of generating synthetic radar data. We used the adversarial training concept to create new RAD images from an image database with 4 types of objects generated through the captured FMWC radar. We can highlighting 4 main contributions of our work. First, the best performance between 3 GAN architectures, traditional GAN, CGAN, and DCGAN, is evaluated in generating synthetic RAD images. Then, assessment of the ability of the generator to produce images good enough makes it difficult for the discriminator to distinguish between real and fake images. And analyze the influence of values of the scores obtained by the GAN when specific parameters are changed. Finally, the analysis of the applicability of the synthetic RAD image generated for data augmentation. For conducting our experiments, we uses a short-range automotive radar operating in a frequency of 76 GHz, with coverage of up to 30 m. Also, the number of images labeled was 2,680 for cars, 2,680 for motorcycles, 2,466 for pedestrians, and 2,475 for trucks. And the generative adversarial networks were used: GAN, CGAN, and DCGAN. Extensive experiments were performed to analyze and compare the GAN architectures. For this, the experimental analyses were divided into 4 phases, evaluating the best performance between traditional GAN, CGAN, and DCGAN in generating RAD images. Assessment of the generator's ability to produce images that can make it difficult for the discriminator to distinguish between real and fake images. Analysis of the influence on the values of the scores obtained by the GAN when specific parameters are changed. Finally, analyze the applicability of the generated data for data augmentation. The Table 1 presents the results obtained considering generator, discriminator, and combined scores for 100 epochs in different flip factor. The flip factor parameter is used to define the fraction of real labels to be inverted in the training of the discriminator. This way, it adds to the real data noise to improve the learning of the discriminator and the generator. In our experiments, the best combined score for the GAN network was 0.6518, with a good value for the discriminator and the generator scores. The discriminator had 0.5312 as a score, and the generator had a 0.3259 score. The best combined score for the CGAN network was 0.6391, with a high value for the discriminator score. The discriminator had a 0.6401 score, and the generator had a 0.3195 score. When the value of one network is close to 1.0, that indicates a better performance over another network. Finally, the best combined score for the DCGAN network was 0.5980, with a high value for the discriminator score again. The discriminator had a 0.6088 score, and the generator had a 0.2990 score. In this case, with a Horst value of generator score in front of both GAN and CGAN generator scores. The final set of experiments included changes in dropout parameters. The dropout technique is essential in reducing overfitting during training. In this sense, the networks were trained with the following dropout values: 0.25, 0.50, and 0.75, and combined with different values of flip factor and 50 epochs. According to Table 2, we can observe an evolution in the network performance after each modification proposed in its architecture. We can highlight 3 results: 4 dropout values of 0.75 and flip factor of 0.10. The combined score value is 0.8728 by CGAN. For dropout 0.75 and flip factor 0.30, the combined score value is 0.7070, but now, by GAN. And dropout of 0.75 and flip factor of 0.10 resulted in a combined score of 0.6731 by GAN again. Despite values 0.8728, 0.7070, 0.6731 of the combined scores being high, these results are not enough to attest to the quality of the new images generated and the ability of the discriminator in the classification. When we observe the scores individually, we have clues about the behavior of the networks and, consequently, the performance and the competition between them. The generator score in these cases ideally cannot be much lower than the discriminator score. Despite the generator generating good images, when the value score of the discriminator is much higher, it can indicate that it still correctly classifies most images. So, if we look at scores of the first best combined score, that is, 0.8728, we can infer that there is a better response from both the generator and the discriminator. Both values are balanced: 0.4904 generator, 0.5636 discriminator, which suggests a slight advantage in the discriminator classification. However, with the excellent generator score, 98% of the ideal score, the discriminator will classify many fake images as real, which is our ultimate goal. The question is, can GAN network generates RAD images with high quality? The results showed that yes. The GAN generated RAD images well, even when a specific object class was specified. We compared the scores of GAN architectures in RAD synthetic imaging generation and concluded that the CGAN score was the better. But, GAN network with the second highest score produced the best score in most experiments. GAN performed lower, so we cut it to the final experiments. This work can open opportunities for new studies related to RAD data classification, such as conditional generations based on vehicle class. Thank you.